All right. All right, good afternoon. Welcome to the NJIT Makerspace. My name's Dan, and I'd like to welcome you to our first MakerSpeak in quite a while. So before we get started, I'd like to tell you kind of what's going on in the Makerspace. Tell your friends what's going on. We have a lot that's been changing around here. First, we have new courses in welding, wood shop, metrology, CNC machining, manual machining, and CNC table routing that will all be running in the next couple semesters. Most of them are running this summer. So check them out on our course catalog if you'd like to take some courses here. We also have a course in prototyping that's been very successful, which we'll start running more sections of. So hope you guys will come and check those classes out. They count for electives in most programs on campus. We also have 2 more MakerSpeaks coming up. Both are focused on additive manufacturing. We have one on April 2nd and one on April 23rd. So keep an eye out for those announcements. We also are supporting some of our student teams here in the Makerspace. We are restarting our solar car team. We have our Formula Racing team, which is a new team as well, being supported out of the Makerspace, our Baja and our Aero team, all working out of here. So come check them out, maybe join them and do some work with them. It's a lot of fun. So I'd like to introduce Mr. Dan Insogna, who is an additive manufacturing professional. He's been in the industry for over 10 years. And he helps people get into additive manufacturing, improve their processes, pick machines, and design all sorts of processes around additive manufacturing. So let's give him a big round of applause. Dan?
Good. Welcome. How's everybody doing today? Yeah? Appreciate everybody making it. So my name is Dan Insogna. I'm the regional account manager for Philips Corporation. Philips Corporation is a global supplier for advanced technology. We're based in Hanover, Maryland, Colfax, North Carolina, and Bensalem, Pennsylvania. Before I get started, I wanted to thank NJIT and Com at your offsite facility for having me. I've had a chance to work with you guys for a couple years and been able to see you grow. So it's been really great. Happy to be here. Topics we're going to cover today, we're going to jump into powder bed fusion technology and hybrid manufacturing. Before we jump in, I'd like to give you a little background on me and explain how I got into additive. So usually when I meet folks, they ask me out of the gate, how in the world did you get into additive manufacturing? It seems like everyone answers it the same way, accidentally. So I kind of found myself in my position, not intentionally out of the gate, but it worked out to be really the best. So how many of you, show of hands, know what a vacuum furnace is or have seen one? All right, that's more than I usually get. So that's a vacuum furnace. So on your right, that's an example of a big vacuum furnace setup. So prior to being at Philips Corporation, I sold vacuum heat treating equipment for the aerospace defense industry. So typically that entails really large parts being craned into a big vacuum furnace for heat treating, whether you're going to stress relieve the parts or vacuum harden the parts. Things like turbine blades in aerospace are a big component. So I wound up getting invited to go down and meet a company in Memphis, Tennessee, a medical company. And we're sitting at their table discussing their application, and one of the engineers pulls out a giant titanium build plate and slaps it on the table. And it was really the first time that I ever saw additive. And I listened to them talk about how they made this part, how they put it in an EOS machine, they 3D printed it, and the end result was they're gonna pull the build plate out and they needed to be able to heat treat these parts to be able to stress relieve them so they don't kind of like fold up like a potato chip. And those parts look like this one. Just like that. So that's an example of a titanium hip cup. That's a pretty standard build that you see in medical. Where vacuum heat treating comes in is if you just tried to cut those parts off the build plate out of the gate, the lips of the parts will fold back, kind of like a Pringle. When you vacuum heat treat them, they relax the part, and then they're able to be cut off and post-processed. So following that project with a company down in Memphis, I started working with a couple other folks, and they were trying to do the same thing. Started seeing metal printing come online. And that really kind of set the stage for me almost 4 years ago as to what was capable. I started seeing additive scale. So at this customer, we wound up walking in the back of their facility into their manufacturing area, and they had 10 machines in a row. They're actually M290s, just like the one you have back in your makerspace. And they had it set up where they could run the machines all night, come in the morning, unload them, put them in the vacuum furnace that I sold them, and then remove the parts and continue on. And that was serial manufacturing. And I didn't realize that that was really a thing until I started working with these folks. And ultimately, that's like what led me to realize, wow, this is a big market. There's a lot of opportunity here. There's some neat technology that I'm not involved in. Maybe we should jump in. And that's kind of how I stumbled my way into additive manufacturing. Everybody seems like they have a pretty interesting way. That's how I found myself in it. So we're going to start off by talking powder bed fusion. So you guys are familiar with the M290. How many of you have seen the M290 in the makerspace? Guys have seen it? So that's a really good example of the most popular machine that's currently being used in industry. To date, there's roughly 1,500 M290s installed globally in the world. So as far as metal printers go, that's the machine that's in use in industry, whether it's medical, aerospace, defense. A lot of folks are using it in automotive for short batch prototyping. It is involved in serial production. I typically see them staged where there's multiples. So to give you an idea, we're actually going to go back there after this talk and you're going to get a chance to see the machine, but that's a prime example of how industry is using and what one of the machine tools is in use. So going back to the time that I was in Memphis at that customer's facility, that was almost 8 years ago. So 8 years ago, I saw serial production. I saw machines stacked in a row. I saw how customers were trying to stage their business where they could have machines running overnight while nobody was there, and then come in, take advantage of all that work that had been done, and then scale their business. How's additive changed now? What does powder bed fusion technology look like 8 years later? It's changed quite a bit. So on this side, that's the M290 that you guys currently have, same machine. Industry typically demands that things get bigger and faster and quality continues to improve. So one big industry demand that's happened over the last 8 years is machines need to get bigger and faster. So a prime example of that is the M300. That's right in the middle. That's a quad laser machine. So they were able to take a single field laser that was built off the M290, design a production system that you're able to almost 4x your production speed. And it also has an auto loader system on it. So it's able to print, shift your build plate out, load a new build plate in, and continue the build. So that was like the next generation move of how do we go faster other than just adding more machines. It's let's give a bigger build plate and let's give a quad laser system. To take it a step further, we needed to go with a bigger envelope. The M400, all the way on this side, that's been one of the most popular large platform powder bed fusion machines that's in existence now. There's roughly 150 installed in North America now. Oil and gas, aerospace, DoD, parts that need to be big. Your build volume's roughly 16 inches by 16 inches, so parts you're pulling off can weigh more than 100 pounds, so to give you an idea of how big they are. Both these machines were built off of the technology of where the M290 started, both from a material standpoint and a scanning standpoint. So just in roughly 8 years, we were able to go more lasers, bigger machine, which in total allows customers to capture more work in those systems. Whether it's a bunch of small parts that you can run in one time or a really large part that you can then post-process. So here's a prime example of some applications that we see quite a bit of. I have a couple examples. We're going to go through a couple of the parts that I brought just so you guys can get an idea of what we can run. But on the left side is a heat exchanger. It gives you details on what was able to be achieved, but a big draw for 3D printing parts, heat exchangers in particular, is reducing the amount of parts in an assembly and the mass of the part. And with 3D printing, you can print just the structure that you need and limit your support structures inside the machine. That part has been around for about 6 years now. It's a whole lot bigger than it looks on the screen. That heat exchanger on the end over here, that's a prime example of what you can do with an M290 system. So that was actually printed vertically on the same machine that you guys have. I believe that part's in aluminum. and you can see how the internal cooling channels are versus the outside texture. That part was taken off the machine with a wire EDM and just bead blasted on the outside. So you can see just in one total, that machine ran overnight, completed that part, didn't require all of the mass that you would have had to do. That would have been a two-piece part to be able to machine the interior and weld it together. Prime example of what you can do with additive. The titanium hip cup that you see in the middle is just like the hip cup that I showed you earlier. The draw with that part is you're able to print a dense part on the backside, and you're actually printing the texture on the outside of that part. There's a reason for that. It's for the human body to be able to adhere to that when you implant it. So if you can picture a hip socket, you have your hip cup here, you have a socket that goes into the back of it, it's bolted together. You need to be able to have human tissue have something to grab onto. So that part's always printed out of titanium. That texturing is actually printed with the machine. So it used to be a three-part operation where you'd have to raw machine the texture in the outside and post-process. Now it's a two-step. Last part, all the way on this side, that's a prime example of like a filter system or a liquid system. Again, with a heat exchanger, it allows you to print internal cooling channels, stops you from having to have multiple assemblies. The big win for this was they were able to remove 10 parts out of that assembly to form one part. And that's really where the cost savings is from a manufacturing standpoint. If you can limit the size of the part, or you can make a leaner part and lessen the overall weight and then take some of the assembly pieces out of it, it's a win. And that's really what we're trying to do with additive. We're trying to build parts smarter. So market tends to demand us to go faster, as I mentioned before. So that doesn't always just mean a bigger envelope or faster. Sometimes that means more laser power. So EOS is the largest powder bed fusion OEM in the world. They are based out of Germany. They have a facility in North America. About 6 years ago, they realized folks kept coming for custom applications, and they need to be able to answer that. So some of those applications were copper printing, which requires a 1 kilowatt laser instead of a 400 watt. So we needed more power. Some of them require a heated print bed to be able to raise the temperature inside that chamber so that material will melt faster. Some folks needed even a bigger machine than what we offered before to be able to build parts taller in a Z-axis. And that's really where the rocket engine industry came in. So you can see on the one side, that AMCM, that's actually an M290. It just has a 1 kilowatt laser on it. So like your machine out there, just more power. Really the main reason for that is to print copper or print aluminum faster just by putting more heat into the powder bed. In the middle is actually the next transition. So dual laser M290, increased production. So for shops that have 3 or 4 M290s in a row, well, maybe they can have 2 and increase their production. That's a way for companies to scale. So we've actually seen a lot of customers that had a single laser M290 upgrade into a dual laser to increase their production. In the middle here, you see FDR, that's fine detail resolution. So it's actually a smaller spot size laser to actually put more detail in parts. So when you start getting into these itty bitty tiny parts, medical industry, for instance, where you want to serialize the size of parts, that's where that machine comes in handy. It has some really cool applications. It was built off of the original M290, so many of the parts are the same. Just allows you to really put some pretty neat components out there. Most of the components I've seen are aluminum in that machine. And now we get to the big ones. So M400 has been the big workhorse system. The 450 came on play for printing rocket engines. And to take it even a step further, the M4K on the end was the biggest one we had. You can print part that's 3 feet tall. So when you start moving into things like rocket engines, where you need big height, that's really the only way to do it. So this project came about with a project from a company called Launcher. Launcher makes rocket engines for the Air Force. Has 2 cool components. They needed to print rocket engines in copper, which we didn't have a way to do, and they needed to print one that was 3 feet tall, which we didn't have a way to do. So AMCM actually took on the first project with Launcher about 3 years ago. They created an M4K system that didn't exist, and the end result was that engine. So that engine is copper, chromium, zirconium. It is, that was the first generation, which was the E1. This is the E2. and they built the first one in Germany. This company resides in California. They actually accepted delivery of the first M4K about 2.5 years ago to print this machine. They've been able to scale their business since. So this is a prime example of innovation. The market demands it. Additive has to step up. You create a custom tool to do it. You produce the part, and now a new machine's born that other people can use. Since this first M4K was sold, I believe we have about 25 of them now in the United States, all printing different applications: aluminum, copper, 316L, and Inconel. And they're going across the board, whether it's DoD, Navy components, parts for aerospace and rocketry. That machine really kind of unlocked the next opportunity for additive. And now you're talking about machines where they're running a part for 2 weeks to be able to print something like that. So it's pretty darn fantastic. That ultimately won them an award with the Air Force, and they've been able to scale. So they have more than one M4K. It's one of the bigger wins that I've seen in a long time. Pretty cool. So now that we kind of covered powder bed fusion, I wanted to jump into hybrid manufacturing. You guys actually have a Philips hybrid at your Comet facility that's off campus. How many of you have seen it or been there? You guys have seen it? Okay. I'll encourage you guys, the rest of you guys, to see it. It's pretty cool. So the story of hybrid is a neat one. Philips was approached by Autodesk in 2020 to build a hybrid system that would essentially utilize a Haas machine and a DED head to print and machine metal at the same time. So the concept is print a raw part, complete your printing, post-machine it, and at the end of the process, you have a part that's done. You don't need to remove it out of the machine and set it back up and remachine it again. So Philips partnered with a company by the name of Meltio. They're out of Spain. We took their DED hardware, wired it into a Haas machine, set the program, the IP, software, and we built the first machine for Autodesk. After Autodesk, we built the second one for the Navy. The Navy actually put that machine on the USS Baton. So it's been printing parts at sea for the last 2 years. So they bolted a Haas machine to the hull of the ship, and they're printing parts with metal and post-machining that part for repair at sea. So since then, the Philips hybrid has been immensely successful. We just installed our 70th Philips hybrid system this year. We have hybrids spread across DoD, academia. We have a bunch in general industry. I'll share about some of the cool part applications in a minute, but the fact of the matter is you're able to take a wire spool that's mounted on the outside of the machine, same spool that you would use for welding wire like a MIG welder, hook it up to the side of the machine, it feeds down through the top of the system, creates a melt pool, and is able to start drawing that part out. So when you start thinking about casting replacements or customized tooling, that's where this machine comes into play. So your facility, Comet, actually has a Philips hybrid. They've been making parts for industry on it. It's a 5-axis machine that has some really great capability. When you get a chance, I would encourage you to go take a look at it. It's a pretty neat tool. So that's kind of the short story. Following the Navy, we were approached by different universities, different industries in automotive, defense, and that's really where we've been able to scale this business, where we've planted a lot of systems. We have customers that did material development. They're able to really build out that industry. It's been pretty cool to see. So following last year, we had the Marine Corps come to us and ask us to design a hybrid with a faster deposition rate. So like we did with the first hybrid, we looked at what the market had, what we could integrate, and we settled on Fronius. So Fronius is in that top corner. That uses a standard welding torch that we integrated inside of our Haas machine like we did with the Meltio DED head. And what we were able to do is leverage the same controls, a very similar deployment mechanism, same software, but increase deposition rate by 6x to 8x faster than what the first hybrid could do. And I have some parts out in front of me that I'm going to pass around, but you can see some big parts that we're able to print with it. When you're talking about putting 6 to 8 pounds of metal down in an hour, you can make some really big pieces. So big valve bodies, big tooling, industry for agriculture, like those big auger bits that you see on the back of tractors, oil and gas industry for fixing broken tools. That's where that fits. So as of last year, we launched the wire arc system and also the laser line system, which is a powder-fed hybrid system to kind of answer industry industry. So we keep talking about what's industry using. Industry's telling us what they need, and we're answering with the technology that works. The hybrid itself, I think one of the big takeaways that we learned is there's a lot of well-trained machinists out there. You guys have a bunch of Haas machines out in your shop. A lot of folks have them in their facilities. They're very good at running them. They have some really excellent operators who are able to train people in about 2 weeks to get their machine up and running. So it's been pretty neat to watch that market grow. So here's an example of a really cool application that we did for hybrid. So bottom of the corner, I'll move out of the way for you guys. This part was actually run at IMTS during a trade show. This was a part for a munitions customer. We took their part. The deal we made was we'll print you 14 parts during the trade show, and at the end of the trade show, you can take them with you. So our engineers took a look at the part, figured out that if we put it in a 5-axis machine, we could print it in 3 different positions, and at the end be able to machine the part and reach inside and actually wiggle the part back and forth and just break it right off the build plate. And that's what we did. So we had customers at IMTS watching this part being built, and then they'd stand there and wait for the machine process to happen so they could watch our operator reach inside the machine and like wiggle it back and forth and break it off. But prime example of you can print the part, you can leave the middle of the part raw like we did, where we didn't machine the middle didn't matter. So very similar to how a casting part is, where you want to just leave the rough outside because it doesn't matter, but you're going to machine the contact points. We simply machine the contact points. And that was a prime example of what can you do with a hybrid and just letting the machine run. In total, it was about a 4-hour process for print and machine, and it required no operator intervention to do it, which was really the turn point for the customer, where they can go in and just hit process cycle start and let the part print and machine and have an end use part at the end. So we ran that one at IMTS. That was a pretty big hit. That was one of many examples. I'll share a couple good ones with you. I think probably my favorite application as of late with hybrid has been for an automotive company. If you guys like diesel engines, you're familiar with how those are aligned. You have giant turbochargers on those engines, and on the back you have a cast iron manifold that comes off that turbocharger, dips down into where the headers are out to the exhaust. Well, that part sees a lot of heat, and historically it's been made out of cast iron. So in working with a customer, they let us know that was a pain point, and they were trying to figure out how can we solve the pain point. They had a casting they had to order that was a 14-week casting. They had to go and machine that part afterwards, and then they scan it to make sure it didn't have any voids. So it's a 50-50 shot if the part's going to be good at the end, and it takes 14 weeks to get it. So we looked at the part. We did a little bit of design tweaks for it. We looked at where the ends match and where they meet up to make sure that it makes sense the way we're going to print it, and ultimately wound up printing and machining a finished part in under 24 hours on the hybrid machine for them. The cool thing about that is that's a company that has never looked at additive before. And I think that's like the most exciting thing that we see in additive. We're having folks that are coming out of nowhere that don't have additive training. They've historically been machinists. They're really interested in what the technology can do, and it's opened up a ton of avenues for people to be involved. I think for you guys in particular, when I was in college, additive was like just kind of coming on, but it wasn't serialized production yet. You are going to have a lot of opportunity if you want to be in additive to be involved in some really cool projects like this, where you can be on the part design side, you can spec which tool makes sense for each application, you can control the process, and ultimately you can improve parts. And as of late, I've seen a lot of really cool part improvement and replacement. We mentioned the wire arc system as our newest hybrid machine. That's targeting casting replacements. So you can imagine these giant valve bodies that are big, like 15 inches by 15 inches, like 100-pound valve bodies. When you talk about looking at how we used to make them versus you can go and print a bunch of different valve bodies in a week in your shop and be able to pull them out of a machine, it really opens up the idea of we can design faster, but we can also deliver a lot faster than ever. So that's kind of what we're seeing in additive. It's been pretty neat. So here's some examples I brought with me today. These are all parts for powder bed fusion. So they've been printed on EOS technology. I'm going to invite you to come up and take a look at them. We'll pass them around, ask me questions on them. I brought a little bit of everything. So we have some copper parts. Copper parts have been, as of late, so more powerful machines, printing complex components. I'm going to throw this up on the screen after questions, just so you guys know what the parts are, and then feel free to ask me. But on this side, these are all EOS powder bed fusion components. We have some aluminum parts, some copper parts. I think the fuel cell, I believe that one's MS1, so we have a little bit of everything. I have an F1 pedal that we actually printed. That's a real part, goes on the F1 race car. We actually, that's actually the better one too. It has all the supports off of it, but you guys will get a chance to take a look at that. Components that are out in front of me, these are all hybrid parts. So the big chunky ones that you see, these are wire arc. And on this side, these parts are all Meltio hybrid parts, like the one that you guys have at Comet. And I wanted to show you the difference on what you can do. So we'll point those out afterwards. I just wanted you guys to get an idea of, like, the Meltio hybrid is going to give you a really nice detail resolution. It's like a 2mm bead width, so you can get some like really nice part finishes, and allows you to like really get inside some channels. The Fronius hybrid's more like a hammer, like get the material down and then machine in your features. And we've kind of showed that down here with the wrenches, where like we printed a raw wrench just as fast as the machine would go, but then we came over and cleaned it up with the machine tool, and it looks great. So it's the tug and pull between, do I want to make this part really fast and machine it nicely at the end, or do I want to put another nicer resolution on it from jump and then clean it up? So that's really what we want to show here, so we'll certainly cover that as well. So with that, I know I covered a bunch of information. We have some things planned. We're going to do the M290 tour so you guys can see the M290. I wanted to leave enough time for us to review these parts. What questions can I answer for you? Yes, sir? Yeah, so laser cladding has been a big thing as of late. So with the Philips hybrid, the fact that you can load multiple materials, it allows you to do two things. You can load two different wires, and for instance, you could print your base part out of, say, just a carbon steel, and you could print Inconel right on top of that part for wear resistance. So when you look at the tooling industry, where a tool's seeing a lot of heat or a lot of stress, instead of using a really hard-facing metal like Inconel, where you would cut it and it would eat your tooling up alive, you could use a softer material as your base material and then print your hardened material on top. And we're seeing that with Stellite. Folks are putting Stellite. So a good example would be a valve body. That valve body seat gets a lot of stress in the inside. You could actually clad in Stellite inside that valve body for wear resistance. And it gives you the option to print with a softer material that's easier to print, that's faster to print, that's a lower cost per part, and then put the really great material on top. And we're seeing a lot of that. We're seeing that with bearings. Tooling industry's big, gears are big. We are seeing a little bit of material cladding with powder bed. It certainly has its challenges. I'm aware that there's some machines out there that they claim that they can print with cladding. They can essentially have multiple materials inside of a powder bed and be able to control it. I'm aware of one customer that's done it successfully with an EOS machine, where they actually took apart, it was a repair application. You could call it cheating a little bit. They started with a different base material, essentially used the top of that part as a build plate, and then just spread the powder across it, and they wound up cladding on top. And that was an Inconel application for nuclear. So it actually turned out to be pretty cool. It's the concept of, hey, instead of throwing these parts out, let's reuse them and build on top of them. And now what does that do for our cost per part? Because we already accounted for that cost on the part originally. So when you talk about not throwing parts out and just simply repairing them with a machine that you have that doesn't need to be really managed by a person outside of just getting the machine started, it really opens up some possibilities. So yeah, good question. The moldy material, we're going to continue to see more of that. If you start seeing some of the high resistance material, Haynes 282, some of the space stuff going on with different alloys, it makes sense to clad surfaces for wear resistance instead of making the whole part out of a really expensive alloy. So yeah, great question. Yeah. Yes, sir.
Are the manufacturers of the systems the same people who make the filaments, the powder? or who manufactures the material, and what's the chemical purity makeup for something to be viable for powder printing?
Yeah, good question. So I guess the additive answer is it depends. We've seen a lot more powder companies coming online. A big demand has been having a powder company that's in the United States. I think the last data that I saw was roughly, I think it's close to 70% of the powder bed fusion business in the world is in North America for manufacturing. So we're doing most of it here. The problem is the supply chain, as we learned during COVID, was over in Europe, which could be challenging. So to answer your question, the majority of powder that's being used is qualified by some of the equipment manufacturers and sold by them. So for instance, EOS, they source their metal powder. They put it through their quality program to make sure the material in lots is up to their standards. And then they ship that material to the customer. So that's our quality control, where we want to make sure that the customer, if they're going to run copper nickel, for instance, on their machine in California, and they're going to run copper nickel on their machine in New Jersey, they're both getting the same outcome. And that's the way that we control quality. There are third-party companies that have been around. Carpenter Technologies is an example. 6K Powder out in Pittsburgh, they're another example. Those folks are bringing on their own powder lines as well, and it's needed. There needs to be multiple suppliers to be able to handle the growth in the industry. And I think the most important thing is everybody manages their quality, which from what I've seen they're doing. Purity-wise, you have a bunch of different alloy choices. So pure copper, our copper is like 99.9% pure, our EOS pure copper. I'm seeing a lot more customers printing with an alloy of copper. So like copper chromium, like I noticed for heat resistance, or some sort of branch off of pure material. That goes the same for aluminum and some of the steels. But yeah, it's a good question. Supply chain, everybody learned the hard lesson of supply chain when COVID happened. It's like, what happens when you don't have all the stock in Texas, or you don't have all the stock in North America, and you have 10 machines running in your facility? Like, that's a lot of powder. So yeah, we're getting better. We're certainly getting better. Great question, thank you. What else we got? Yes?
Hi, sorry if you mentioned this already, but do you have any hybrid, do you have any hybrid systems that are tolerant of reactive materials? And if so, are they tolerant of flood coolant?
Yes, so good question. Short answer is yes. We are printing a decent amount of titanium with our hybrid in wire form. Doesn't have an issue. The Meltio hybrid itself has an argon blanket that is essentially deployed out of the head, and it just blankets the part, so it doesn't fill the whole hybrid chamber. That's proven to work really well. If it's a component that isn't going to get post-machine and it can't have any oxygen contact at all, that requires an extra step. We call it a boot. You essentially just cover the part with really it's like a seal. So when you're printing, you're not allowing any oxygen to get into the part. Seeing a lot of titanium printing. A couple reasons. The titanium sourcing is coming from everywhere, so you're getting different raw stock. We can control a lot easier in wire feed, because you can go and order a titanium spool from your local supplier. Comes with a data sheet. Most of the spools are 30-pound spools like you use for welding wire, so it's much easier to control. And you don't have some of the waste as well. You use roughly 99% of the material that you're going to feed into the hybrid. So I'd say that's probably the number one reactive. I've seen a little bit of aluminum printing. We're actually going to do some aluminum printing with the wire arc system. So that'll be the other reactive material that probably is second place to titanium. Yes?
Why develop the powder laser printing when you guys already have a powder wire or a laser wire printing?
Yeah, so powder bed fusion and hybrid manufacturing complement each other really well. So in some cases, you can only use powder bed due to part design. So are you talking about powder bed fusion like EOS compared to hybrid, or are you talking about the addition of the hybrid?
The hybrid system.
So why laser line?
Or why powder in the hybrid system?
Yeah, good question. So the number one answer is some materials we can't turn into wire. they're too hard, or they don't play nicely in the machine. Laser cladding has been around for a while. We have a picture of that laser line system. We actually ran this at the show. That's actually a spline. So we started off with just a round piece of stock. We started the machine on one side, and I don't have a video of it here, but it's going crazy fast. And the concept is duplicating what you could get on the back of like an agricultural machine. If you've seen those giant augers that are like this big around, well, if you have to build that spline out, you have to go fast. You also need ability to have a thin bead. And with that laser system, we're actually able to deploy powder down through that head, melt it very quickly, and keep the machine moving. So just like we learned with Meltio, where it's great for high resolution, small and medium sized parts. The Fronius is really great for your medium and large sized parts when you want to throw a lot of material down. The laser line's great when you have laser cladding operations like that, where you need to go fast and you just can't get the deposition rate out of our other technologies. Yeah, so good question. We have a design on the bottom of the table that when you're printing, it shields the powder away, and the waste powder falls in the bottom of the machine, and then it's just pushed out of the system like you typically would push chips out of. So yeah, there is waste. The waste is going to depend on how big of a part that you're using, because that's going to dictate how much powder is going into the machine. It's not as clean as what the Fronius or the Meltio system is, because really your only waste is when you feed the wire down through the head initially, you snip off the end to give yourself a good starting point. From then on out, whatever wires fed into that melt pool is used, just like your FDM machines that are up front where you feed that filament through. You're 99% utilization of your material. I would say on a small scale, you probably have 10 or 15% material loss with the laser line system. The play with that is, if you're doing that application, you can't do it with powder bed, or it's not cost effective to do it with a powder bed machine. And the hybrid still makes sense because you're typically going to build on another part. You're not going to build a part from raw. So it's a part dependent technology for sure.
Thank you.
Yes, sir. Good questions.
For some of the parts, are you ever building on top of existing geometry, like in hybrid, maybe CNC first, bring it over to additive, and then back to finishing?
Yeah, good question. Yeah, so repair is awesome. We talk about a lot of repair applications. I had a really cool one with a company. They use dyes to make stamping for 3M products. So if you know like 3M foam, you have all sorts of safety gear and it has 3M on it, it's super spongy. They actually use the dyes, and they have all sorts of different dyes, spinning dyes and top cutting dyes. And we did an application with them where we took the worn out die that they had that didn't keep its shape, the edges were flat. And we're actually able to cut them off, build on top of that part, and then they would just put that part on a grinder and be able to face off those edges. So like that's a prime example of it. Another one is just broken tooling. Folks can go take a broken tool, put it in the machine, load the original CAD drawing for that part, cut the broken piece off, come in with your print head, build up. We typically build up 10 or 15% over net shape, and then come in with your machine tool and clean it up. If you can find justifications for hybrid that way, the cost per part is outstanding because you're already starting with a part that you have. So yeah, we've seen that. I'm actually have a cool application with a customer in North America now. They're doing nuclear components for nuclear reactors on submarines, and they're using hybrid to do it. And the play is with Inconel that you can print the bearings in Inconel and machine it and cut those parts off with a wire EDM and have the replacement parts that no longer exist. And it's this whole concept of, well, if I can make a part that I didn't have out of a stronger material and not eat my tooling up, and I don't have to stock the material, or I could take parts we already have, cut off the broken piece and build them back up again, you're starting to round the bases to machines making machines. And we're pretty excited to see that one day. We joke about it all the time about like how long is it going to take for like an additive machine to start making like 50% of another one. I think that's probably not that far away.
Yeah. Thanks.
Yeah, awesome question.
So I got to ask, when do precious metals enter the chat?
Yeah, so they have entered. We're playing around with some different materials. It's challenging with it because you need the R&D time to be able to develop the parameter set. And that means you need the material that's expensive and hard to come by. And we're starting to see more of that. So you start getting into like refractory materials. You start getting into component creation where we're trying to look at like what makes sense to do. And I think the biggest challenge I see in powder bed is if you have to build a big part out of a rare material, you start venturing into recycling older parts into those materials. And we're starting to see that concept happen. A couple of the powder companies that we were talking about that are in the States, they're starting to design material that has a percentage of recycled material in it. It's a concept of like, you can't just keep printing parts and throwing them out. Additive is great because you're trying to maximize as much of the material as you can. Well, if you can recycle old parts, reuse them, turn them back into powder again, and then use them in machines, like that's the holy grail. So reactive metals are there. They certainly have their challenges, but so did the material when we started. So yeah, I would say if you blink, there's a new material coming on the market. So we're starting to see more of it. Yeah.
So you mentioned machines making machines. Do you see a role for AI where you can just put in the specs you want and it decides how to do it, what machine to use?
Yeah, so AI is gonna be something. I'm not quite sure how long it's gonna take. We kind of took our first stab at it at EOS about a year ago. I think IMTS, it was either IMTS or Rapid, they released something called Smart Fusion. And Smart Fusion is a software that goes in and reads the design of a part, examines how it's currently being made, and identifies improvements, and then spits out that redesign to the machine, and you can print it. And the conversation turned into, well, you have parts that we've been making for 30 years that were designed by senior engineers, and you have a software that can go in and reduce up to 70% of the existing supports that had been in that part. Prime example is this part here. This is actually built with Smart Fusion. So this was an existing part that had a lot more supports on it. Smart Fusion looked at it. It not only limits the supports on the part, but it actually takes meat out of the part that doesn't need to be there while still maintaining strength. So that was like the first inkling of we saw like you could take a drawing, plug it into this system, and AI looks at how it's designed, how the printer reacts, how the structural integrity of that part was laid out, removes as much material as it can compute, and then pushes it to print. And then we start getting into the concept of like, what if you had a factory do that? What if you could run through a 100-part dialogue list and push them to all the machines on your floor and have them print? So we're gonna see AI do some crazy things. If I had to guess, in 2 years from now, I'll be telling you a different story. Yeah, super exciting. Anybody else? Yeah, I think we're good.